Hello everyone, welcome to Tech Talk Universe. Over a century ago, in 1894, American physicist Albert Abraham Michelson, the founder of the University of Chicago's physics department, gave a speech at the dedication ceremony for the Ryerson Physical Laboratory. In his speech, he claimed that while it is never safe to affirm that the future of physical science has no marvels in store even more astonishing than those of the past, it seems probable that most of the grand underlying principles have been firmly established, and that further advances are to be sought chiefly in the rigorous application of these principles to all the phenomena which come under our notice. In hindsight, this statement sounds wildly off the mark. However, at the time, given the incredible achievements of physics in the 17th, 18th, and 19th centuries, thanks to the contributions of pioneers like Galileo, Newton, and Maxwell, it seemed quite reasonable. What we now refer to as classical physics offers a nearly comprehensive description of the world around us. No one could have predicted that the 20th century would bring groundbreaking theories like quantum mechanics, which would completely revolutionize our understanding of the universe. This all started with a seemingly insignificant study concerning the light emitted by objects. To understand this, we must first grasp the concept that all objects are constantly emitting electromagnetic radiation. This includes you, me, the screens we're using, and every other object in our daily lives. Why does this happen? One primary reason is that objects are composed of atoms and molecules, which are filled with charged particles, such as electrons. These charged particles constantly disturb each other as their temperatures change, releasing energy in the form of electromagnetic waves in the process. Aside from this reason, there might be other sources for the emitted electromagnetic radiation, but we'll leave those out for now. Anyway, throughout our lives, we've learned that there are three ways heat is transferred: conduction, convection, and radiation. Radiation, in this case, refers to the energy released by objects in the form of electromagnetic waves. So, what characteristics do these radiant energies have? To understand this phenomenon, we need to find an appropriate model to study. Ideally, this model should absorb all light from its external environment and only emit electromagnetic radiation due to its temperature. This way, when we measure the emitted electromagnetic waves, we won't be influenced by reflected waves, and we can be sure that the radiation originates from the object itself. Such an ideal object is called a black body. After all, black objects appear black because they absorb light from their surroundings and reflect little. In our daily lives, the closest approximation to an ideal black body is the sun, which is not black at all but rather extremely bright. This is because we can be quite certain that the light emitted by the sun primarily originates from itself, rather than reflecting light from its surroundings. Another example would be an empty cavity with a hole, where electromagnetic waves emitted from the hole are similar to blackbody radiation. This is because all light entering the hole enters the cavity and is not reflected. A blast furnace used for smelting iron has a similar structure. Up until this point, everything seemed like a typical physics research topic. Strangely enough, in the late 19th and early 20th centuries, when scientists had a comprehensive understanding of electromagnetism, they faced difficulties using previous physical theories to accurately deduce electromagnetic wave radiation from black bodies, despite having obtained experimental data. It was at this point that classical physics began to show cracks. The radiation emitted by black bodies, as we know it now, can be represented by a graph similar to the one shown here. The vertical axis is proportional to the power of the energy radiated by the black body, while the horizontal axis represents the wavelength of the electromagnetic waves emitted by the black body. Under ideal conditions, blackbody radiation depends only on the black body's temperature and is unrelated to its shape or material. Taking blackbody radiation at absolute temperatures of 3000 K, 4000 K, and 5000 K as examples, we can see that as the blackbody temperature increases, the power of the radiated energy also increases. At the same time, the wavelength at which radiation power is highest shifts towards shorter wavelengths and higher frequencies. To explain the observed data of blackbody radiation, physicists began to apply everything they had learned up to that point, attempting to find the correct black-body radiation curve. In 1896, German physicist Wilhelm Wien derived the black-body radiation formula, which became known as Wien's approximation. On the other hand, between 1900 and 1905, British physicists Lord Rayleigh and James Jeans also derived their black-body radiation formula, known as the Rayleigh-Jeans law. When comparing these two formulas, one can see that each of them is accurate only on half the spectrum. Wien's approximation is precise for the high-frequency range, while the Rayleigh-Jeans law is more accurate for the low-frequency range. The latter also predicted that radiation intensity would approach infinity as the frequency of electromagnetic waves increases. Wait a minute. Infinity? That's unreasonable, as real black bodies do not emit an infinite amount of energy. Both explanations were not accurate enough. Ironically, just a few years after Michelson's 1894 statement suggesting that there might be nothing more astonishing left to discover in physics, the magnificent achievements of classical physics were partially overshadowed by the mystery of black-body radiation, and nobody knew what was going on. It was at this critical juncture, when classical physics faced a dilemma, that a certain man stepped onto the scene. In 1900, Max Planck derived his black-body radiation formula, which became known as Plancks Law. Planck hypothesized that within a black body, there were numerous charged oscillating units called oscillators. He further assumed that the energy of these oscillators could only be an integer multiple of a fundamental unit of energy. This fundamental unit of energy is expressed as E equals sine hv, where it is proportional to the frequency, v, of electromagnetic radiation, and the proportionality constant, h, is called Planck's constant. In other words, the energy a black body radiates is based on hv as a fundamental unit, and is a countable sum of such quantities. This means that the energy has been quantized. Based on the above assumptions, Planck successfully derived a formula that matched the experimental observations of black body radiation. Planck's equation combined the advantages of both Wien's approximation and the Rayleigh-Jeans law, providing high accuracy for both the low and high-frequency ranges. When comparing the solar radiation spectrum observed at the top of Earth's atmosphere, the data align very well with Planck's formula. Unfortunately, Planck considered the energy quantization he assumed to be merely a mathematical tool for derivation, not realizing its profound physical implications. Regardless, Planck successfully solved the problem of black-body radiation and obtained a formula consistent with observations. Even now, we still use Planck's formula to describe black-body radiation. Moreover, there are many practical applications in everyday life derived from this understanding. Since objects at different temperatures emit electromagnetic waves with distinct characteristics, we can determine an object's temperature by measuring the emitted waves. During the pandemic, many places installed screens displaying images similar to this one. These devices only measure a specific wavelength of infrared radiation. Infrared radiation is part of the invisible light spectrum and is the wavelength with the highest power in electromagnetic radiation emitted by room temperature objects. By analyzing the infrared radiation emitted by our bodies, we can determine our body temperature to a certain extent. Of course, this approach has limitations. First, we are not pristine black bodies, and second, environmental factors may interfere, causing some degree of error. With the study of black body radiation, we can standardize the relationship between a black body's temperature and the color of the visible light it emits. The rainbow background represents the range of visible light. As the temperature of a black body increases, the emitted electromagnetic radiation in the visible light spectrum shifts towards cooler colors. When buying light bulbs, you'll see color and temperature indications on the packaging. If you want warmer light, look for a bulb with a lower color temperature, around 2000 K. In the late 19th century, when black body radiation research boomed, it coincided with the Second Industrial Revolution. Significant advancements in steel smelting technology emerged at this time. Traditionally, Steelmakers relied on their eyes to gauge the temperature of steel based on its color. However, a more accurate temperature assessment would undoubtedly be helpful. Germany, a leading country in the steel industry, made many contributions to the study of black-body radiation. This may have been driven by academic curiosity, but it also aligned with the social needs of the time. In summary, Planck introduced the concept of energy quantization and successfully used mathematical formulas to describe black-body radiation. This achievement laid the foundation for the development of quantum mechanics. Although Planck himself did not grasp the profound implications behind energy quantization, another trailblazer, Albert Einstein, built upon Planck's ideas and offered a deeper interpretation, which is the subject of our next story. That's it for this episode. Remember to subscribe to Tech Talk Universe's channel and turn on the notification bell so you don't miss the latest episodes. This is Tech Talk Universe. See you next time.